Today we start talking about angle modulation. Now, earlier we considered amplitude modulation as a means of transmitting messages. And that means we are putting information about the message signal into the amplitude of a carrier. In figure A here, you see a carrier wave, which is a sinusoid. And in figure B, you see another sinusoid, which in this case stands for the message waveform. In C, you see something that you recognize as double sideband amplitude modulation, double sideband suppressed carrier amplitude modulation, because the information on the message signal in B has been embedded into the amplitude of the carrier wave. In figure D, you see something different. What's going on in this figure? Take a look at the amplitude of the waveform in B. As the amplitude is high, the frequency here is high. When the amplitude is going through zero, in this case, which corresponds to here, it appears that the frequency is lower. When the amplitude is at its lowest value, it corresponds to the amplitude of the carrier, the frequency of the carrier being even lower. So lower than the original, actually. So the instantaneous frequency of the waveform, the carrier in part A, has been modulated according to the amplitude of the message signal in figure B. So we are carrying information through changing the angle or phase of a carrier wave. This particular example corresponds to the modulated waveform u of t equals AC cosine theta of t, where theta of t is a time varying phase that is derived from the message signal. Why do we use angle modulation? One important benefit is it has better noise immunity than amplitude modulation. Angle modulation has better noise immunity in general, and we will analyze this later on. The main drawback is it tends to use more bandwidth. So when you can trade off bandwidth for high noise immunity, angle modulation types are preferable. Now, the difficulty in the analysis comes in because modulators, angle modulators cannot be modeled as time invariant systems. Because for the simple reason that u of t, as you saw in the previous slide, contains frequencies that are not present in the input signal m of t. You know, an LTI system very well. At the output of an LTI system, you do not see frequencies that are not present in the input, right? But you do see new frequencies that are not present in the input at the end of angle modulation. So angle modulation is not an LTI operation. They are also nonlinear, okay? Time varying and nonlinear. Okay, so you're not very, in general, in electrical engineering, we do not spend a great deal of time analyzing systems that are time varying and nonlinear. So this will be interesting. Okay, fortunately, all of this analysis is ages old, more than 60, 70 years old. And it is very well established. And we will review some of this analysis in order for us to understand better concepts for modern day RF transceiver front-end design. As you know, especially for IoT systems, people are developing new technologies for power efficiency and for transmitting over long distances. And all of these ideas are coming into the design of new standards from scratch. Okay, so it will be useful to understand angle modulation techniques, their analysis, and the related trade-offs in terms of power efficiency, bandwidth, noise immunity, etc. So let's look at this modulated waveform, U of t, AC cosine theta of t. Now, it has time varying frequency, but we can talk about a frequency at time t. You know, we could approximate this frequency at time t by taking an average of the amount of phase change in an amount of time of duration delta t and divide by 2 pi times delta t, because this theta of t is in radians. So in order to convert to cycles per second, we need to divide by 2 pi. Right, let's consider the limiting case. Suppose we are taking delta t to 0. Okay, this corresponds to differentiating theta and dividing by 2 pi. We will call this thing fi of t the instantaneous frequency. And this instantaneous frequency is going to be a function of our message signal. Let's see a very simple example of an unmodulated carrier carrying no message at all. So in this case, we have 2 pi fc of t plus a constant phase. What is the instantaneous frequency? Clearly, it's fc, and that's that, and there's no message. Okay, now let's see the first kind of angle modulation that we're going to study, phase modulation. In phase modulation, we put the message signal into the phase in this form. So we take the message, multiply it by coefficient Kp, that is called phase sensitivity in this case. And then we put it on top of a 2 pi fct linear phase component, basically. So what we obtain is the modulated signal is AC cosine 2 pi fct plus kpm of t. So the message is directly put in as an additive term into the phase of the sinusoid. What happens to the instantaneous frequency? Simply differentiate the phase and you obtain fc plus kp over 2 pi times the derivative of the message. Any questions so far? All right. So let's talk about frequency modulation. In frequency modulation, we as the name suggests, we directly modify the frequency itself rather than the phase. So consider a sinusoid whose phase, whose frequency is modulated by the signal. We add a suitably scaled version of the message signal to the frequency itself. Okay, so what will happen? The instantaneous frequency is derivative of the phase. Therefore, the phase is the integral from infinity, negative infinity to t, right, of the instantaneous frequency. When we do the integration, you will see that we have 2 pi fct in the phase plus kf times 2 pi times the integral of the message. Interesting. So the integral of our message is going into the phase. So an FM modulated signal looks like this. AC, that's the carrier amplitude as before, cosine 2 pi fct plus kf 2 pi integral of our message. Already you can sense that the math is not going to be pretty because there's the integral of the message inside the cosine as an argument. It's going to have very fun properties though. Any questions so far?
Hocam, integrali neden eksi sonsuzdan alıyoruz?
That's the fundamental theorem of calculus, right? Because
Tamam, pardon, şimdi anladım.
I mean, if we started from any infinite part, we would have to subtract out finite time. We would have to subtract out the value of m at that time. Okay, yeah. So now, here are some visual examples. This is an unmodulated carrier. This is a message signal. FM would be, you can just look at the frequency, instantaneous frequency, and the instantaneous frequency will change exactly like the message itself. When the message has high amplitude, the frequency is high. When the message has a low amplitude, I mean, the message goes down to lowest possible value, the frequency goes down to the lowest possible value. This is pretty clear in time domain. If, on the other hand, you look at phase modulation, it's perhaps less direct because our message is modulating not the frequency but the phase. So it is sort of less direct to, to see the mapping visually. However, we will see now a very direct relationship between FM and PM. Now, PM is this. It's easier to essentially express analytically, kind of harder to see visually. And FM, in contrast to PM, is harder to express analytically, easier to see visually. To generate an FM signal, we are first integrating the input signal, the message signal. And then, if you notice, we take the integrated message and put it into the phase, just like such a term. So essentially, after integration, we're putting the integrated message to a phase modulator to obtain the FM signal. So we can obtain FM by putting not the message, but its integral into the phase modulator. Similarly, we can obtain a PM signal by putting the derivative of the message to a frequency modulator. So if you go back to this visual example, if we differentiated the message and then modulate the frequency of the carrier, we would obtain this. So think about it. When is the derivative highest? It's highest, well, around here, for example. So we obtain the highest frequency. So again, it's highest around here. Okay, so as I said before, angle modulation is nonlinear. So scaling or superposition do not hold for angle modulation. What does this mean? Suppose M1 is modulated as FM or PM, and the output signal is U1 of t. And M2 is modulated and we get U2 of t. If we scale M1 and put it into the phase or angle, frequency modulator, do we get a scaled version of U1? We don't. You can easily convince yourself by putting, using the expression. Similarly, if we add M1 and M2, do we get U1 plus U2? We don't. So homogeneity and additivity do not hold. It is not a linear operation. Notice that if we do not have a carrier, if the carrier is suppressed, AM is linear. Okay, suppressed carrier AM types are linear. So SSB, double sideband suppressed carrier, they're linear. They're therefore easy to analyze in frequency domain. On the other hand, the spectral analysis of angle modulation is going to require some approximations. So in order to begin understanding the spectral analysis, we will start by going to special cases. So both FM and PM signals can be easily understood if we study square and sawtooth waves as modulating waveforms. So consider this example. MT is a square pulse. The square pulse is going to modulate the frequency of a sinusoid. How can we do that? Consider a sinusoid whose frequency is in this case, well, it's hard to tell, but from 0 to 2, it is higher than average, and from 2 to 4, it is lower than average. Okay, how about phase modulation? Notice that we showed that phase modulation is nothing but integrate the message, differentiate the message, and then use it. Let's go back. Differentiate the message and use it as frequency modulation. Or you can directly think about the phase modulation. In this case of a square pulse, it's easy to think directly. The message is scaled and added to the phase. Okay. So the phase, there's going to be a phase shift, an abrupt phase shift at time 2 here. Because suddenly, from message goes from 1 to -1. Okay, and depending on the beta, the modulation intensity, the phase shift is going to be increasingly abrupt, right? So this is actually a common modulation that is used in digital systems, digital modulation systems, as you will see later on. Okay, because it's phase shift keying, PSK. Some of you may have heard about it. Now think of the sawtooth wave. Okay. Now, how about frequency modulation with this? Now, the analogy to phase modulation may come in handy, because if we differentiate this, we will obtain the signal on the left. So when we differentiate it and use it as a, going back, when we differentiate it and use it as frequency modulation, we should obtain the PM signal. Let's see, differentiate, use it as frequency modulation, we obtain the PM signal. Okay. On the other hand, when you use it in the as an FM, when you modulate it with FM, the frequency will keep ramping up. It will be very high from 1, 2, 3, and then it will go down again. Okay, I think this gives a fairly good idea. So now let's start the mathematical analysis. Okay, we will start by the easiest case. And in fact, this easiest case is going to be pretty much the only case that we'll analyze exactly. Single tone FM, when the modulating signal is a tone. Specifically, the modulated signal is some A sub m times cosine 2 pi fmt. So the message signal has frequency f sub m. We will also say it has bandwidth fm. In general, of course, our modulated signal is going to have, it's not going to be just a sinusoid, it's going to have a certain bandwidth. In this case, though, and I didn't draw this very well. In this case, FM is going to be the message bandwidth. All right, so now in the FM, we have 2 pi kf times the integral of m of t from negative infinity to t, right? What is the instantaneous frequency? Well, fc plus the derivative of this, which is simply kf m of t. Okay, but m of t is a sinusoid, so our instantaneous frequency changes like a sinusoid. So what does this mean? This is our message signal. Message signal has like varies from kf am. So basically, let's go back. So cosine varies between -1 to +1. Okay. So the variation delta f is then the maximum frequency is kf am. Okay, it can go delta f up or go down by delta f, right? Kf am is the maximum frequency deviation. All right, so that is KF AM. So our instantaneous frequency varies around FC, which is the level, which is the frequency of the carrier, by plus or minus delta F. So plus delta F minus delta F. Okay. And the period of this variation is 1 over Fm. Now, let's see. This is our instantaneous phase. And as you know very well, when you integrate a cosine, you get a sine. And the 2 pi Fm comes in here. Okay. So when you cancel out the 2 pi's, we have delta F over Fm appearing as a multiplier to the sinusoid. So the instantaneous phase is 2 pi Fct plus some beta times sine 2 pi Fmt, where beta is delta F over Fm. Interesting. Now, I can also express u of t as AC cosine 2 pi Fct plus beta sine 2 pi Fmt by using this angle inside the sinusoids. So we have really gotten rid of the integral, and we've expressed the FM waveform in the case of a single tone message signal as a sinusoid whose instantaneous frequency is changing sinusoidally. Now, the behavior of this signal is very much dependent on the value of beta. Okay, remember, beta controls how strong the frequency deviation is. Okay, when beta is small, the resulting modulated waveform is called narrowband FM. How small it has to be, we will later discuss this. When beta is large, it's called wideband FM. Okay. Now, let's begin by analyzing narrowband FM when the message signal M of t is a single tone. For simplicity, suppose that the carrier amplitude is unity and the message signal, let's see, the modulated waveform is cosine WCT. Here, WC stands for 2 pi FC. Plus beta sine WMT, right? As we obtained in the previous slide. Now, this is cosine A plus B, and we can use the identity cosine A plus B is cosine A cosine B minus sine A sine B, right? So cosine WCT times cosine beta sine WMT minus sine WCT sine beta times sine WMT. All right. Okay, so what do? If beta is small, and that is what we mean by the narrowband FM limits, well, inside the cosine, we have an argument which is close to 0. Think of the Taylor series expansion for cosine. It is 1 minus x squared over 2 factorial plus x to the 4 over 4 factorial, all even powers of x. And when x is small, higher order powers could be neglected. Similarly, sine x is x minus x cubed over 3 factorial, etc. So if beta is small enough, beta is sufficiently small, then we could approximate cosine as 1 and sine as the identity function. What are we really doing? If you look at cosine, cosine looks like this. And if we're around 0, if you're here, cosine, I'm sorry, I need a different marker. So around here, cosine is pretty much constant at 1 if you take very small values of x. Similarly, we talk about sine. Sine goes like this, and around very similar small values, it's like the identity function. So that's the approximation we're using. It'll just make this trivial because if you look at this, it is going to reduce to beta sine WMT, and this whole thing is going to reduce to 1. So guess what we get? Cosine WCT minus beta sine WMT sine WCT. Now we'll further use one more trigonometric equality to convert this to the second term to cosine Wm plus Wc minus cosine Wc minus Wm. Okay, so we have 3 cosine terms. One of them is at Fc. The other 2 are at Fc plus Fm and Fc minus Fm. Does this resulting modulated signal remind you of something that you've seen in the previous lectures? Yes, please, Mutlu. Right, it looks like the spectrum of double sideband suppressed carrier. Now, how about single tone phase modulation? Oh, yeah. Right. So we're both wrong. It looks like double sideband with the carrier, right? Because this is the carrier. And this is the double sideband, except there is some difference in the spectrum, but essentially it's in the same family. So this is an AM signal, conventional AM signal. So narrowband FM is almost equivalent to conventional AM. So that's probably I mean, since it's equivalent to conventional AM, obviously then it does not come with the noise immunity and efficiency properties. Now let's examine single tone PM. The message signal is a single tone. And the phase is simply a scale version of the message. Therefore, the modulated signal is AC cosine theta of t, which is 2 pi FCT plus kpam cosine 2 pi FMT. Okay, in this case, we call this part kpam, the modulation index for phase modulation. So in general, the modulation index can be viewed for PM and FM together. In PM, we have kpm of t coming as a phase term. And in FM, we have 2 pi kf times the integral of the message coming in as a phase term. Now, in the PM case, the modulation index was defined as Kp times the maximum amplitude of M of t. Remember, Kp AM in the case of a single tone message signal. But in general, if M of t is not a single tone, the maximum amplitude is whatever the maximum amplitude is, and then we define the modulation index as Kp times that. The modulation index is going to be very important in the spectral analysis of angle modulated signals. So here in the PM case, the modulation index is quite different. Remember, in the sinusoidal case, we have 2 pi kf over 2 pi fm. But in general, when the message does not have to be sinusoidal, we will have instead of fm, the bandwidth of the message signal appearing here. And for now, we define beta f as kf times the maximum amplitude of the message signal divided by w. Well, the clear analytical reasoning for this will become more apparent to you later on. At the moment, I'm just giving this to you as a definition. But it sort of makes sense if you think about it, because beta, the modulation index, controls sort of how much the message itself affects the phase. Okay? In PM. And if you look at FM, again, beta controls how much the phase is affected by the message waveform. In our derivation with a single tone message signal, beta turned out to be delta F over FM, where delta F was, let's see, delta F is KFAM. So we had beta here equal to KF times AM, which is the maximum amplitude of the signal, divided by FM. Now, in the case of a non-sinusoidal signal, general signal, okay, the corresponding beta is KF times M of t maximum amplitude divided by W. Okay. I know it seems like we're introducing a lot of notation, but we're pretty much at the end of our notation here. Any questions? So let's revisit narrowband angle modulation considering FM and PM together. In general, in angle modulation, we have a carrier waveform whose frequency is modulated by theta of t, where theta of t is time varying and it is proportional to the message, or it's proportional to the integral of the message. So, well, express the cosine A plus B as cosine A cosine B minus sine A sine B. And in the narrowband limits, such that beta P, or in the case of FM, beta F, is small, such that theta itself is much smaller compared with 1. What is the significance of 1? 1 is the maximum value that the cosine itself can get. I marked the wrong thing here. Okay, so when theta is small enough that first order Taylor series expansion is not a bad approximation, the modulated signal, it can be approximately written as AC cosine 2 pi FCT, where cosine phi of t is approximated as 1. And sine phi of t is approximated as phi of t itself. So we have AC phi of t sine 2 pi FCT. So this is a conventional AM signal, except in place of a, right, I mean, let's remember the conventional AM, right? Let's write here, UAM of t is AC cosine 2 pi FCT plus AC M of t some other value, AC Ka M of t cosine 2 pi FCT. So instead of a positive cosine, we have a negative sine. Other than that, though, it is spectrally very similar to a conventional AM signal. Whether it is PM or FM doesn't matter, because we're doing single tone. Single tone means when you integrate, you still get a single tone. So narrowband FM, narrowband AM are conventional AM. So that should be a hint that what we want to consider FM as a different modulation with superior benefits, we need to consider the wideband case. If it's not wideband FM or PM, then it's not worth really going through the trouble. Just use conventional AM. But we will spend a little bit more time on the analysis of narrowband FM, regardless, because it's going to give us some tools to analyze and understand the wideband case. Any questions so far? No? Okay, so U of t is 2 pi AC cosine 2 pi FCT plus 2 pi KF integral of the message, right? Now let's let Z of t be the integral of the message. In the narrowband case, this is small, so we can express this as AC cosine WCT minus 2 pi KF AC Z of t sine WCT. Now, this is not necessarily conventional. I mean, this is Z of t is not necessarily a sinusoid in this case. Okay. So let's look at the spectral properties. The first term is a cosine, so we get 2 delta functions from there. And from the second term, let's see the second term. Z of t times sine. Sine in the spectral domain gives us 2 impulses, and multiplication with Z of t corresponds to convolution with those. So as a result, we have ZF minus FC minus ZF plus FC. The minus is coming from the fact that it's a sine, not a cosine, remember? And the 2j is also coming from the fact that instead of 1 over 2, we have 1 over 2j because this is a sine, not a cosine. Now, if there is no DC component in the message, which it's not going to be anyway, because why communicate a DC? It's true for digital and analog modulation alike. Z of t is, as you know, the integral of the message. If it had a DC component, we wouldn't be able to integrate it, right? And therefore, because of the identity of Fourier transforms, where the integral is a Fourier transform, which is 1 over j 2 pi f times the Fourier transform of m of t itself. Okay, we can express the above as AC over 2 delta f minus fc plus delta f plus fc plus kf AC over 2. The j's will cancel and the 2 pi will cancel with 2 pi. Conveniently, we have this expression. Okay, remember, this is the narrowband limit. In general, FM cannot always be characterized like this. This is the narrowband limit. Okay, so let's take a look at the spectrum visually to get an idea. We will suppose this is the original M of F scaled by F. We will have M of F scaled by F shifted to the right and to the left by FC. And we will have a carrier. So it looks like AM. And if you ignore the carrier, it looks like double sideband, suppressed carrier. So it has two sidebands. There's a large carrier, okay, therefore a low power efficiency. And it will also have low noise immunity. We will see this later when we talk about noise. All right, any questions so far? Now, we will make use of phasors again in the rest, because we have sinusoidal signals, and we can always think of a cosine as the real part of a complex exponential. So we'll do that. What is the frequency of our complex exponential? 2 pi fct. I mean, what is the phase, I'm sorry, of our complex exponential? 2 pi fct plus beta sine 2 pi fmt, right? So this is the phase of our complex exponential, and our signal, our cosine, is simply the real part of e to the j, that phase. Somehow, I mean, we can put the AC, the constant, in here, doesn't matter. It could be outside the real part or inside the real part. It's real anyway. The reason we grouped it with the e to the j beta sine 2 pi fmt is that we will call this the complex envelope of the signal. The other term is coming from the carrier, and this is coming from the message itself. Okay, so the complex envelope of our message signal, message component, is e to the j beta sine 2 pi fmt. Okay. Notice that as this is a complex exponential, it is periodic with period 1 over fm. Okay. The fundamental frequency is fm, f sub m. Therefore, it has a Fourier series expansion. Okay. So we can find the Fourier series coefficients then. So how do you find the Fourier series coefficients? You integrate against the corresponding harmonic term over a period and scale by the period. What is the fundamental period? It's Tm, which is 1 over Fm. Okay, so this is our U tilde of T with fundamental frequency Wm in radians per second. And to find the nth Fourier series coefficient, we integrate with, essentially we are taking the inner product with the nth order harmonic in the series. And this integral minus pi to pi, with a change of variables, you can show that this is minus pi to pi. So do this as homework. Change of variables as exercise. You can show that this integral is from minus pi to pi, 1 over 2 pi, e to the j beta sine x minus nx. It looks like something that is not going to be evaluatable in closed form, and it isn't. This thing is known as the Bessel function of the first kind of order n. You may have seen this before. So Bessel function of the first kind of order n. Well, what is it to us? Well, we will use what is known about these Bessel functions to get some ideas about the approximate bandwidth of our FM signals in general. So now that we found the Fourier series coefficients, we can represent our complex envelope as a Fourier series, where the coefficients are jn's and going from minus infinity to infinity. Okay. Okay. So this is the e to the j 2 pi n fm term, and this is the Bessel function of order and evaluated at beta. Okay, so what does this mean? This is bad news. Why is it bad news? Because it means, look, how many spectral components are there here? How many spectral components? What is the spectral content of our FM signal or of our PM signal? Infinite. We have an infinite number of spectral components. So its bandwidth is theoretically infinite. Okay. Originally, we were doing the narrow band limits. In the narrow band limits, only 2 of these Bessel functions are non-negligible. And we got something like AM that we know how to deal with. But in actuality, when we are not in the narrowband limit, meaning when beta is not very small, then FM and PM signals theoretically are spread out over an infinite bandwidth. Okay, you may say, is it really infinite? The good news is essentially the significant components are going to be over a finite bandwidth, and we can neglect the tails. So the rest is going to be the art of determining the effective bandwidth of an FM or PM waveform. Now, let's go back to the theoretical expression of summing infinitely many Fourier series terms. But for simplicity, we are still considering a sinusoidal message signal. So our modulated waveform can be expressed in this form: cosine 2 pi fc plus n fmt. What is fm? Fm is the frequency of the single tone message signal. Okay, 2 pi fc plus n times fmt. Wow, so we have a component at fc, we have a component at fc plus fm, we have a component at fc plus 2 fm, fc plus 3 fm, etc. And we also have the negative versions. All of these spectral components. Now, what are their weights? Their weights are controlled by these Bessel function values. Let's look at the Bessel function values. How fast do they decay? The Bessel function, this is the Bessel function of order 1, a first kind of order n. Order 0 looks like this. Starts at 1 around 0 and then oscillates. Order 1 goes like this. Order 2 goes like that. Order 3 goes like that. Now, order 3 is here. Now, we do not need their values for all values of beta, because we have a particular beta, right? Suppose beta is here. Suppose beta is very small. Then look at these terms. J0 is high. J1 is perhaps appreciable. J2 is quite low, and J3 is negligible. And after everything after 3 has negligible amplitude. So that's great. It means that if our beta is small, the number of spectral components that are significant are going to be limited. In fact, the narrowband limit corresponds to beta around 0. Beta around 0. And that means only J0 is non-zero in that case. Hence, we have only one spectral component. Hence, we get the conventional AM. Any questions? I mean, only one spectral component. Let me quantify that, further qualify that. When beta is close to 0, what do we get? We have Jn of J0 of beta, which corresponds to a cosine term at 2 pi fc, at frequency fc. And we also get J 1 of beta, giving us FC plus minus FM. Okay? Beta close to 0. If beta is exactly 0, then we do not have modulation anyway. Right? If beta is exactly 0, then we're just transmitting the carrier. If beta is small but non-zero, we get the narrow band limits. As beta grows, if beta goes toward 5, for example, we're talking about actual wideband FM. Any questions? Now, due to the presence of an infinite number of non-zero harmonics, FM technically is not band limited. Due to the nonlinearity, spectral characterization for general message signals is complicated, but single tone analysis yields insights and basic rules of thumb that we then approximately apply to other more general message signals. Most importantly, we're able to characterize an effective bandwidth through single tone analysis. Now, next we will talk about the spectrum of single tone FM, but I propose we give a break here and maybe review what we've done so far.